very exciting new experiments. Line trends.
Okay. Thanks, Bill. Yeah, thanks to all the organizers for the great workshop and for having me. Let's see, I have kind of a 50-50 mix of hardware or experiment and theory. And the hardware I thought people might be interested in, even though there's probably not a lot of experimentalists here. I tried to keep it at a pretty high level, but please feel free to interrupt me if you have questions or if things don't make sense. I'm happy to take more time for it. And so this, the story I'll tell you is work going on right now at Quantinuum. It's all kind of hot off the presses. And I've been working on some of the theory details for what's going on with Matt DeCross and Reza Hagjenas, who are both at Quantinuum. And so the title, Simulation Complexity of Circuits with Random Geometries, is, I guess, relatively descriptive. We'll get into some details. For people that aren't familiar with our kind of approach to quantum computing, so it's the so-called quantum charge coupled device approach to trapped ion quantum computing. So this was pioneered largely at NIST and also other places, a couple decades ago. And the basic premise of how this works is that we store qubits in ions, and the way that we achieve the ability to gate between arbitrary pairs of ions is that we can actually physically move these ions around, and we do that above the surface of a trap that looks like this. So the computer I'll tell you about today, this so-called H2 computer, it looks like this, and you can see this kind of racetrack-like thing down the middle, and the ions actually kind of float, like 70 microns off the surface of that trap. They float in a ring, so they're kind of laid out in like a 1D circle roughly. And the details don't matter a lot, but for anybody who thinks about this stuff or knows, our qubit is actually just two kind of joint electronic and nuclear spin states in the electronic ground state of a ytterbium ion. And the only thing you really need to know that's important is that the coherence time, if you put a qubit in a superposition of these states, it's sometimes called a clock state because the energy difference between these is very stable. And what that means is a qubit pointing in the x direction, say, will stay pointing along the x direction for on the order of 10 seconds. And that is long enough for us to do experiments without dephasing of the qubit being a particularly relevant source of error.
How big is that?
Oh, yeah, good question. Well, let's see. I'm kind of guessing here. I'm like pretending to be an experimentalist, but I think it's probably about 1 centimeter from here to here. So I'm sorry, am I getting? No, that's too large. It's probably less than 1 centimeter, but it's in that ballpark. Okay. Bill asked me to give this talk initially tomorrow, and then he told me that it should be today. And that cut my time for writing the talk about in half. And so I don't know if I'm going to get to the end of it. And I wanted to, okay. Well, I wanted to make sure I thank the people who are actually doing the experimental work before, running out of time at the end of the talk. So these are the people that are kind of, this is really just a subset of the many people, including, engineering staff that are working to build this H2 quantum computer, build and operate. Okay. All right, so things I will not talk about, maybe unfortunately for this audience, is computational complexity, largely because I don't know almost anything about it. I talked to Bill. Bill, did I get this right? So Bill told me the complexity theory, it's all about making absolute statements of difficulty regarding specific experiments at a specific scale, and then nobody will ever simulate the experiments I'm showing you. Okay, that was the way I understood it, but what I'll actually talk about is really two things. One is some exciting progress in scaling up this trapped ion quantum computer to the point where computational difficulty is at least on the table. And the other thing is I'll talk about the difficulty of simulating the types of circuits one can realize with this architecture, at least from a practical standpoint, using kind of known state-of-the-art methods. Okay, so here's now a cartoon view of this same ion trap. And so initially this was launched with 32 qubits, and in principle there's actually 8 places where you can do quantum gates by shining lasers over the surface of this trap. But right now we only use 4 of those locations shown down here. So qubits have to be in one of these 4 spots to apply gates to the qubits. And I won't go into any of the details. These are laser-based so-called Mulmer-Sorensen gates. That's our 2-qubit gate and stimulated Raman transitions for single-qubit gates. So, you know, one thing to keep in mind is just kind of a detail, but it kind of adds to the amazingness in my mind that this thing actually works. Is that in addition to qubits, you know, to do high-quality 2-qubit gates, it's important that the ions be very cold, so they're not vibrating in the trapping potentials that they're held in. And to get them cold without destroying the quantum information that's stored in them during a circuit, it's important to have a co-trapped sympathetic coolant ion, and we use barium. And then you can laser cool barium at frequencies that the qubit doesn't see. And then you can sympathetically cool the ions and keep them cold enough to do deep circuits with high quality gates. So this is actually, you know, many more qubits than, or many more ions than shown in this trap. And I'll show some preliminary data for this machine operating now with 56 qubits. So upgrading this machine is largely just a matter of figuring out all of the, you know, relevant kind of transport primitives and you know, control voltages to apply to all these electrodes to get more qubits stored and, you know, coordinated, kind of moving around the trap in the way you need to get them into the right places to do gates. Okay. So I'll give you a zoom in of what an actual quantum circuit looks like in a device like this, just looking at kind of 4 qubits now in 2 gate zones. And so you know, take a circuit, I guess I just had 3 qubits, sorry. So take a circuit that looks like this. So a red, green, and a blue qubit. And you know, this is one of the gate zones, this is the other, and let's imagine they start off located like this. You know, the first thing we'll do is laser-based state initialization to get them all in the 0 state. When we want to do single qubit gates, I've drawn it so the red and green qubits are already in the right places. So single qubit gates, again, are just laser-based operations. And now the first non-trivial thing is a 2-qubit gate. To do a 2-qubit gate, well, so since this was already asked, I'll give you a sense of scale. This distance between these gate zones is about sort of, it's like roughly millimeter scale. And so that's very far from the standpoint of doing 2-qubit gates. They're really too far apart to talk strongly enough to have high efficiency gates. And so to do a 2-qubit gate, like the C0 gate that's called for, what we do is actually move the qubits together until they're co-located in the same trapping potential. Then you can do a laser-based gate. And okay, so if you look at this circuit, the next thing that happens, it appears inconsistent with this kind of 1D geometry we have, because now you need the red one to be gated with the blue one. And the trick is that they're only kind of confined to 1D. We're able to actually rotate them past each other like this. And then you can move the red one and the blue one into the same location, and then, you know, execute this gate like that. So in that way, you can kind of imagine building up primitives like that to execute arbitrary gates in a quantum circuit. Okay. Let's see. And yeah, so measurement's kind of the same story. I'll just move on now to giving you a picture of this more in kind of at scale in the context of this H2 machine with 56 qubits. So, you know, if you hand me a circuit that's kind of densely gated, like every layer of gates in the circuit has n over 2 2-qubit gates in it, you know, it doesn't matter what qubits those gates are between in the first layer. It might say, you know, do a C0 gate between qubit 1 and qubit 14. Then what I'll do is the qubits are laid out in some way initially. I'll just label whatever ions happen to be next to each other 1 and 14. So they're already in the right places to do the gates. So one round of gates, that's the initial round in a quantum circuit, so all these little wires are gates, can always be applied to nearest neighbors. So the way we do this is we do these 4 gates on the 8 qubits in the gate zone, and then we just kind of Rolodex this whole thing through until we've done all of the gates in batches of 4 and gone through the entire layer of gates. So that's one layer of a circuit. So for sort of an arbitrary circuit, the next gates might have no connection to the 1D layout that you sort of put the qubits in to do the first row of gates, the first layer of gates. So it could be something complicated. So the first step to being able to do this for us is to actually sort the qubits in the trap such that all the gated pairs are now next to each other. So that can be done in an automated fashion. And once you've done it, you can now place all these qubit pairs co-located if they need a gate in this layer in the trap, and again, just Rolodex through and apply all the gates in this next layer of the circuit. And then you just keep repeating that as you move through a circuit. So that's the sense in which we can, you know, execute circuits with arbitrary kind of connectivity of the gates. And let me just give you kind of a quick rundown of some of the most important sources of error in this device. So the first one to call your attention to is this 2-qubit gate error. So everything's given in units of 10 to the minus 4. So what this number means is through kind of standard randomized benchmarking techniques, we can implement something like a CZ gate. That's kind of what our native gate is logically equivalent to. We can do that with roughly 2 times 10 to the minus 3 error rate. Okay, so you can think of that as the gate is perfect, kind of 998 out of 1,000 times, and the other 2 times it spits out garbage. The other primary source of error that we have is, I mentioned that we can kind of randomly permute these qubits into new locations to do arbitrary gate assignments, and that's true. There's 2 prices you pay for that. One is it takes time, and 2 is in the time when that's happening, you can have errors just because the qubits are idling, and they can be subjected to kind of magnetic fields that aren't perfectly under control or whatever other kind of noise you have in the experiment, and that can cause errors on the qubits. And so we like to do an experiment that we call transport single qubit randomized benchmarking. And what it basically amounts to, it's relatively simple actually. So imagine a circuit where you have, say dense layers of 2-qubit gates, single qubit gates, and then you randomly permute the qubits before repeating that in a new layer of 2-qubit gates. We take a circuit like this and we run it, except we delete all the 2-qubit gates. Okay, so what this circuit does is it just does rounds of repeated single qubit gates on the qubit with lots of transport in between, as if they were going through a complicated circuit. And this kind of incorporates both single qubit gate errors and all the kind of memory errors you might worry about that could happen during transport as a separate contribution to add to the actual error from the 2-qubit gates themselves.
How you transport them from, if they're not nearby, you skip that.
I did skip that, yeah, and I don't have a great slide in this talk to tell you about it, but more or less, here, I can go quickly back to this. In this picture that I had on the first slide, every one of these little, rectangles is an independent electrode with a wire that goes down, out the back, and we control the voltage on all of those electrodes. And so we can apply time-dependent voltages to more or less just sculpt the potential over the surface of the trap. And then by controlling those time-dependent voltages, you can create, harmonic confining wells, and you can move them all over the place, combine them together.
And for these numbers that you stated on your last table, do you always, before every 1 and 2-qubit gate, laser cool?
But you don't really need to do it before the single qubit gates. But for the 2-qubit gates, yes, we laser cool the barium before all 2-qubit gates, yeah. That's pretty important to get fidelities kind of in that range, yeah. Okay. Did that roughly answer your question? Okay. Let's see. So what I wanted to emphasize here is that, in a densely gated circuit like this, these are really the primary drivers of our error budget, these 2 things. And you can add them together to think about kind of an effective, total error per pair of qubits per 2-qubit gate in a circuit. And if you add these 2 sources of error together, it's about 2 times 10 to the minus 3. It's not that much larger than the 2-qubit gate. And so when I say we can, make a circuit with arbitrary connectivity, what I really mean is that this number is almost that number. It's a little bit bigger, so we pay some price for that connectivity, but it's marginal at this scale. Yeah.
Do you know if the error that you commit while transporting is the same for linear transport and for when you cross the 2 ions? Is that figure included in this?
That's a great question. I don't know the answer. I would say that most likely they don't spend a whole lot of time in a typical, well, actually, I don't know. I guess I should say I really don't know. I mean, we kind of group all these things together into this one metric that builds all of it in, but it would be hard for me to break it down. Thanks.
Yeah. If you don't have much swapping around to do it, one of these layers, is it quicker, or does it, if you have a more complicated permutation, does it take longer?
Yeah, that's a great question. So it generally runs quicker, as you'd expect. If you hand it in a circuit with a natively 1D geometry, it runs much quicker. Yeah. Okay. So, we've done a bunch of tests with this machine to validate that this kind of effective, per 2-qubit gate error that we measure from these 2 component benchmarks is actually consistent with what you'd expect or what you measure in running complicated circuits. So these are just 3 examples of a few different benchmarks, including random circuit sampling on 2D circuits and 2 benchmarks that involve using kind of random connectivity. And the details aren't so important, but what I want to point out is just that if you kind of infer from modeling what 2-qubit gate error is consistent with the results of these experiments, that's what's in this column, it's in pretty good agreement with these component benchmarks. So that's telling you that there's not a bunch of other kind of crap going on in complicated circuits that's not accounted for by measuring these sources of error. Okay, so let me move on to a description of some recent work looking at random circuit sampling now, rather than in a 2D geometry, which is mostly what's been done, with some exceptions that maybe Misha will tell us about, to random circuit sampling on circuits with random geometries. And so here's my very kind of cartoonish picture of random circuit sampling. You know, the task is you are handed some description of a random unitary, and the goal is to draw samples from the output distribution that's induced by applying that unitary to the all zero states. And so, you know, on a quantum computer, you'd actually apply the unitary, you'd make measurements, and you'd get out some bit strings from that measurement. And, you know, roughly speaking, the idea of random circuit sampling is that not all outcomes are equally likely. There's some structure to the probabilities of observing different bit strings. And so you can subject the data that you get to statistical tests. So it could be, for example, linear cross-entropy benchmarking, as Google did. And you could test to see whether the more probable outcomes are actually, you know, being obtained with sort of, you know, more than typical probability. And, you know, the overall thinking is that, you know, in practice at least, if you can achieve very high scores on a benchmark like this, consistent with having a circuit that outputs almost, you know, state with almost perfect fidelity, that they're, you know, kind of spoofing such a test or scoring well on such a test seems to be about as difficult as just directly simulating the circuit in that regime. So that would be kind of the premise of random circuit sampling being a difficult to simulate kind of experiment. Let's see. So, you know, what has typically been done is to do random circuit sampling in the following way, where you take some circuit that actually has a very non-random spatial structure. So I'm drawing it in 1D because it's simple, but it turns out it's actually really not a good idea to do random circuit sampling in 1D. And people have done this in 2D. And so, you know, in this case, the gates are all laid out in a very structured way, and the only thing random is the choice of what single qubit gates, say, you insert between your 2 qubit gates. Now, so what I mean by doing this in a random geometry is as follows. So the way that we define a circuit on a random geometry is first we draw a random, so say we want a circuit on n qubits, that's depth d. We draw a random d-regular graph with n nodes. Okay, so in the case of a depth 3 circuit on 6 qubits, you would draw a graph that looked like this. And now you take this graph and you assign an edge coloring to it. So that means we color the edges in such a way that only no 2 edges of the same color are, you know, impinging on the same node in the graph. So there's just 1 edge of every color for every node. So in this case, we have a 3 coloring of this 3 regular graph. And in general, you can always color a graph, you know, a regular graph like this with usually d colors, sometimes d plus 1. But for simplicity, you can just think about it always being d colors. And so the way you turn this into a circuit is pretty simple. So you basically, you know, because of the nature of an edge coloring, the fact that, you know, edges of the same color never touch the same qubit, you can assign 2 qubit gates to these edges, and you're guaranteed that those gates can always be applied in parallel in the same layer of the circuit. Okay, so basically you take a color and you assign that to a layer of a circuit, and now you have a decoloring of a d-regular graph that's become a depth d circuit in that way. Yes, so here time is going up in this circuit, yeah. And there's many ways you could choose your gate set, but for us, it's relatively natural to just use our perfect entangler for the 2 qubit gates, so it's basically a CZ gate. And we just use, you know, hard random SU2 gates, but you could use sort of your favorite gate set for the single qubit gates. Okay, so this is kind of how we induce a, you know, circuit of random geometry by drawing, you know, random regular graphs. Now I wanted to, I mean, the sort of the reason that this is interesting to be able to do this is that it appears that there are kind of significant implications of geometry on the cost of exact simulation. And so I'll talk a little bit about how that actually shakes out, specifically for these random graphs or circuits based on random graphs. And I don't know if this statement will be controversial at all. I didn't mean it to be a controversial statement, but I think it's true, or people would agree, that the best known general purpose method for simulating kind of an arbitrary quantum circuit is to convert that circuit into a tensor network and to do optimized contraction of that tensor network. And at least if you want to simulate something with very high fidelity and no structure, it's sort of generally about the best one could hope to do with known methods. And so the way this would work in practice looks like this. So now imagine 1D quantum circuit, so time going, say, from bottom to top, and all these green things are 2-qubit gates. So, each of these gates ingests 2 qubits and spits 2 out, and you can think of 0, 1 for each qubit as just an index that lives on the leg of a tensor. So this really is just, a description of a tensor network that I'll draw a little differently now, with the tensors being these circles and the legs coming out of them being the qubit wires. And one other thing that it makes some of the description of what follows simpler, but it's not actually that important, is that you can turn this into a structure where the qubit wires and the gates both correspond to edges in the tensor network by just doing singular value decomposition on these tensors to split the gates into 2 rank 3 tensors that are joined by a wire like that. So now your gates are wires, the green wires, and your qubits are the black wires in this tensor network. So, if you go to contract this tensor network, what that means is summing over the indices of the tensors that are connected by edges. It turns out that the cost of doing that is very highly dependent on the order in which you do those contractions. So you can kind of roughly think of, contracting a tensor network as just kind of eating up these small tensors into bigger blobs of, higher rank tensors with more edges sticking out of them. And if you start doing this, like you eat up all the ones that are in here into a single monolithic tensor, just the cost of storing that and doing any operation on it is going to be exponential in the number of edges that are sticking out of that object. So I've kind of drawn a red dot on every edge, and the cost is now exponential in the number of red dots. So this is generally true. And you can kind of think of 2 extreme limits then of how you might go about contracting an object like this. So one of them is you could kind of move from the bottom to the top. So you can move in a time-like direction. And if you do that, what you see is that at every point in this contraction where everything below here has been absorbed into one big tensor, all the wires sticking out are just qubit wires. This is just state vector simulation, right? You're just storing as a tensor the wave function that has emerged at this time in the circuit, and you're propagating it forward. So the cost of doing this should be exponential in the number of qubits, unsurprisingly. And you can think of this kind of contraction as sort of cutting qubit wires when you're forming these tensors, and it's really the fact that you have to cut n wires that makes it E of n expensive. Okay, so another strategy would be to contract the tensor network sideways. So to contract everything to the left of this, bipartition, for example. And if you do that, you can convince yourself that now the only things that cross this partition are the gates. And so the number of red dots is just set by the depth of the circuit. So if you contract it sideways, you expect in 1D the contraction cost to be exponential in the depth, but independent of the qubit number. This is all, well-known stuff. Let me generalize this a little bit to more than one dimension. So if you had, say, a 2-dimensional system, so like a square that was evolving up in time in the circuit, now a sideways contraction would correspond to kind of moving a sheet or a hypersurface from, say, left to right in this diagram as you do the contraction. And you could imagine that these tensors are scattered throughout this bulk here, and the number of legs sticking out through this red surface inside this green cube, it's going to scale like the depth times the length of that cube. And the length is just the number of qubits to the 1 over the number of spatial dimensions. So if you then just count up, this times this, what you end up finding is that you get a cost that should be exponential in d times n to the d minus 1 over d. So n to the d minus 1 over d is just the surface area of a spatial bipartition of this d-dimensional thing. And in general, if you have kind of fixed depth and very large number of qubits, you expect in general this to be much lower than this. So kind of asymptotically for large qubit number at fixed depth, this is the way you expect the cost of tensor network contraction for simulating a circuit to scale. Okay. So I want to write down kind of 2 measures then, or 2 ways of thinking about the cost of doing a tensor network contraction. So the first is to just count how many floating point operations would it take to kind of aggregate all of these tensors until you get at the end of the day an amplitude for a particular outcome of the circuit. And so you could take the cost in flops, and you could divide it by the number of gates. So that's n over 2 times the depth, and take the log 2 of that, and call this thing this script n an effective qubit number. And the reason it's an effective qubit number is you could think I might have a circuit with a very large n, but at some finite depth in some geometric locality. And that circuit, through tensor network contraction, is only as hard to simulate as the worst case, state vector simulation cost of simulating script n qubits. And the reason for that is just that if you take, 2 to the script n, what you get here is the state vector cost that you'd expect for that. I mean, you get the actual cost. So this is just saying the cost of your tensor network contraction is as expensive as the cost of state vector simulation on that. So it's helpful to also think about not just this effective qubit number, but also kind of a density of the complexity of contraction. So if you normalize this by the number of qubits, this is now just telling you that the cost, it's telling you what fraction of your qubits are contributing to the cost in the sense of worst case state vector simulation. So if C is close to 1, then it's telling you that your circuit is deep enough that there's really nothing better you can do than state vector simulation. If it's much smaller, it's telling you that there's other smart contraction strategies that are better. So let me just kind of call out this in particular. So the way that, this argument that I gave about the kind of, hypersurface area in doing a sideways contraction would tell you that this cost should always be, it's at most 1 because it's sort of the density of the with respect to the maximum cost. But it could be less if n is asymptotically, larger than d in some way. And what this kind of quantity in here is telling you is the surface area of a spatial bipartition divided by the qubit number. So in general, for large n, this will always be much smaller than 1, and it will set the actual optimal cost. Now, for a random circuit, a random geometry circuit, the gates are laid out like this, right? So we have all of these nodes, and the gates are just kind of a mess. They go all over the place. And so the way to think about a spatial bipartition, it's not really a spatial bipartition anymore. It's just a generic, bipartition of this graph into 2 different sets of nodes. And so the right, kind of notion to replace this spatial bipartition with is the edge boundary of a bipartition. So what I mean by that is if I just draw, a line that separates the qubits into 2 halves, how many gates or how many edges cross between one half and the other? Okay. And again, to get this kind of effective complexity density, we're going to take the size of this edge boundary, kind of optimized over all partitions, and we're going to divide it by n. And it turns out this is a very well-studied quantity in graph theory. So people call this the isoparametric number. If you kind of minimize the size of this edge boundary over all possible bipartitionings, and it's been known for 30 years or something like that, 35 years. That as you take n large with very high probability, this edge isoparametric number is larger than a constant. It does not go to 0. And what that means for us is that as we take n going to infinity with high probability over the family of random circuits we're studying, the contraction density will not go to 0. Will be bounded below by a constant at any finite depth that turns out greater than or equal to 3. So that's kind of markedly different than circuits in any kind of geometrically local setting. And so let me show now an attempt to actually quantify the contraction cost of these different circuits and show you that this scaling kind of pops out. And the way we do this, many people have developed different ways of trying to find optimal contraction orders for tensor networks. We worked with Johnny Gray, who developed this Cotangra package to do all of these estimates with Cotangra. But it should be kept in mind that these are all heuristic attempts to minimize the cost. So strictly speaking, everything that's plotted should be viewed as kind of an upper bound to the cost or the contraction complexity. It could, in principle, be lower. But empirically, we don't really know of any way to achieve lower results. This is kind of the best that we know how to do. We're making an honest attempt here. And so here's a plot of this complexity density now for random 2D circuits as a function of qubit number and of depth. And what you see is that these contours have a shape that looks like square root of n. And that goes back to the argument I was making before. Effectively, it's telling you that as you grow the qubit number, if you keep the depth fixed asymptotically, this contraction complexity density goes down, and you have to grow the depth kind of comparable to square root of n to keep it of order 1 or to make the circuits maximally hard to simulate. So this is a known property of 2D circuits, and it shows up in this numerics. Let's see, and we can do the same thing now for circuits based on random graphs. And we find empirically evidence of the result that I just told you could be proved based on sort of known graph theory results. So the fact that these contours are flat is telling you that if you fix the depth to some sufficiently high value and then take the number of qubits going to infinity, the fraction of qubits that can contribute to the worst case simulation cost is actually staying constant in a random geometry. average degree.
Because
The-
everyone's connected to everyone, right?
Right, so the degree is actually fixed. It's always a regular graph. So the degree of everybody is set by the depth of the circuit.
Oh, just by the
Yeah.
matches.
Exactly.
Okay, matches.
Yeah, exactly. Okay. So if you look at this, one obvious consequence of these contours being flat is that if you want to make the circuit deeper until every qubit is contributing to the hardness of simulating it, you have to get up into this black regime where C is of order 1. In a random graph, you don't have to go as deep as you would have to in any kind of finite dimensional lattice. And in practice, what we generally find is that for 56 qubits, the number that I was telling you, I'll show you data for that we can now load into this trap. You need to get roughly up to a depth of 12, something like 10, 11, 12 before the cost really saturates to the worst case kind of state vector simulation cost of simulating 56 qubits. Okay. So what I want to show you now, I made this statement at the beginning about tensor network contraction being maybe the best way, the best general purpose method for achieving high fidelity simulations of circuits. So the obvious question is, what are the fidelities that you expect to come out of a circuit like this? Are they actually high? And so I want to show some evidence of what one might expect them to be. And the way that we, sort of our preferred way of characterizing this is through a technique known as mirror benchmarking. So actually, somewhat recently, Google used a very similar technique that they referred to in the language of condensed matter physics and called it a Lau-Schmidt echo. But this is a little bit different than what they do, but it's a very similar idea. So in the case now of a depth 3 circuit, we just take that circuit and then we mirror it. So across this dotted line, all of the gates are just the inverses of what's shown below. And then what should come out of this circuit, if there's no noise, is whatever you put in. Okay, so you can just look at the end of the circuit at how many times, if you run it a bunch of times, do you measure the input state at the output. And one caveat is that for these kind of gates on the reflected part of the circuit, we also do a technique called randomized compiling. And the idea of that is to try to remove the effect of any coherent errors that you might worry are somewhat nefarious, right? One obvious way this procedure could fail is if all of these gates are actually badly wrong, but they're also wrong in the same inverse way on the inverse side, right? The state here could have no fidelity with respect to what was intended, and you'd still get the right answer out. And so randomized compiling is sort of a way to prevent there from being coherent errors in the circuit that could have that effect. And so we've done simulations of this kind of process using a very detailed noise model for our device. So this noise model, I'll just say a couple words about it. One, it's based on cycle benchmarking data for our 2-qubit gate that essentially measures the individual contribution to the total gate error of different types of Pauli errors. So if you consider the gate error channel to be a stochastic Pauli channel, then this measures the fraction of all the different Pauli operators. So we have that data for our 2-qubit gate. And then, we know that the memory errors that happen to the qubits in between gates is probably partially coherent and partially incoherent. We worry the most about the coherent fraction, so I'm just going to make the worst case assumption that it's all coherent in doing these simulations. And so with that error model, we now simulate the return probability of a circuit like this. And here I'm showing it for 24 qubits. So you're relatively limited, in what you can simulate and do this. And there's 3 curves here. So first of all, this black curve in the middle, this is just actually, measuring the fidelity of the output state in the circuit, just through the numerics. This dashed line is an estimate of what you might expect the fidelity to be if it were 1 anytime there were no Pauli errors and 0 whenever there were. So this is what Google in their 2019 paper kind of established or referred to as a gate counting metric. We just take the number of gates that are in the circuit. We just take the fidelity of the 2-qubit gates, this effective per 2-qubit gate fidelity, and we raise it to the power of the number of gates that are in the circuit. And you can see, at least in these simulations, it's a pretty good estimator of the actual fidelity. Now, this purple curve in here is the simulated mirror benchmarking return probability, and you can see that it's also, a pretty good estimator of the fidelity, although they kind of miss in opposite directions, and that's for reasons that can be understood, actually. So that's all kind of as expected. One other thing I'll say about this is that we tried to be pretty careful since you can't simulate very large systems. And we actually do these simulations at many different system sizes where we scale the error rate such that at every system size, the probability of an error happening in a single layer of 2 qubit gates is the same for all n. And what that means is that this decay should look the same when you rescale your model that way. And what you find is good collapse. So the fidelity as a function of n is well collapsed when you scale the error this way. And so you expect that if you could continue these simulations out to 56 qubits, it would continue to look like this. And we do the same thing. This was for the actual fidelity, but we do the same thing for the mirror benchmarking simulation. So we see no real evidence of any kind of independence with this kind of rescaling, suggesting that the statements made on this plot at 24 qubits about all of these being good estimators of the circuit fidelity, both gate counting and mirror benchmarking, should hold out to larger qubit numbers. Let's see. So I have here some very preliminary data showing what actually happens when we run these kind of mirror benchmarking experiments on this machine with 56 qubits. And so a couple of things worth pointing out. One is, you have roughly an exponential decay that's consistent with this curve here, which is from a gate counting argument, again, just based on the measured fidelity of the 2 qubit gates and the memory error. The other thing worth pointing out is that as you get out here to the depth where, so the kind of shaded region to the right is meant to be an indication of where the cost of simulating these circuits by tensor network contraction should be basically as hard as just doing a state vector simulation of 56 qubits. As you enter this region, the actual sort of estimated return probability or estimator of the fidelity is kind of somewhere between, say 0.2 and 0.4. So it's something like, you could think of this as a statement that at this depth where the circuits become maximally hard to simulate, about 30% of those circuits execute without even a single error happening on any of the gates anywhere. Yeah, good question. It's the full depth. So for example, at 12, this means that a depth 6 circuit was mirrored to produce a depth 12 circuit.
I don't see how you concluded that was exponential.
Oh, yeah. I mean, what I should say is that we put an exponential.
I think it's exponential, so.
Fair enough. It was a slightly sloppy way of saying it. What I should say is that this curve, this black curve, it is an exponential, okay, with a base set by the measured gate fidelities. And it is not too bad a fit with the error bars. Are there discrepancies with exponential? I mean, I'm not claiming that there will not be any, but at this level of precision, it's relatively consistent.
Yep. Do you have correlated noise? And would this matter and show up here? Correlated noise.
So without knowing exactly what you're concerned about or what types of correlations you're worried about, I would say,
global magnetic field fluctuation.
Yeah, so global magnetic field fluctuations is actually in this modeling that I showed you. That's basically what's assumed for the error model. So I tried to assume kind of a worst case scenario for correlations of the noise as contributing to the memory errors. I mean, there's many other sources of correlations one could worry about, like maybe when you do 2 qubit randomized benchmarking, you don't detect somehow that the fact that you're applying a gate over here impacts the fidelity of the gate over here. I mean, we try to look at all of those things and measure, whether there are any forms of crosstalk, and generally see it to be very small. But it's definitely something that we think about and worry about. Yeah.
What's the reason you put preliminary there when the L bar is actually smaller? In what sense did you put preliminary?
But because I don't want to be held to anything that I said today. No, it's just, literally this data was from like 3 days ago. So it is kind of hot off the presses. So it's just a disclaimer that the dust is still settling kind of. But it does appear possible to run circuits of this depth on this machine with that return probability.
So do you have a sense how scrambling, at what point is it kind of, because it's not a long, 6 is not a super long depth, right?
Yeah, right. So we have done some studies of this, and I think it depends a little bit on what you mean, but in general, one thing I can say is that for the circuit size we can simulate, we believe that the output distribution is pretty well approximated by Porter-Thomas at depths above like 9 or 10. So out at the depths where we're sort of able to run these circuits with high fidelity, we think that they are scrambled.
Which would like 9 or 10 twice times 2.
Yes, although the mirror benchmarking being a good indicator of fidelity doesn't actually require that the circuits be scrambling.
Yes,
So Yes, they're two separate questions. But I guess what I'm saying is that you might, even though this 0.12 is just two mirrored depth 6 circuits, I don't think you would worry about the fact that the circuit at depth 6 does not produce a Porter-Thomas distribution accurately. You wouldn't worry about that causing a disconnect between mirror benchmark return probability and the fidelity of the circuit. So you would then expect that if you ran a forward depth 12 circuit, you would expect to see a comparable fidelity to this for a circuit that was scrambled. Let's see, any other questions? I thought I maybe saw one other hand up, but it went away.
So did you consider going beyond 20? Because, some previous supremacy experiments have very low fidelities.
So I think we could, I think, yeah, you can tell, like with a reasonable amount of data, we have error bars that, like pretty significantly exclude this from zero. So if you ask, could you run deeper circuits? I think we could. I guess we didn't see a whole lot of reason to. We had to stop somewhere in 20. The reason we picked 20 was basically that it was like significantly more than 12 and not so much more that the data taking requirements become large. But yeah, I think, we could push that a little bit. Okay, let's see. We're getting close to the end of the time, which is good because one of the consequences of Bill asking me to give the talk today was I didn't finish my slides. So this was meant to be, I don't know, with 2 minutes left, would you rather I give like a lightning round on approximate circuit simulation, or should I just kind of wrap it up? People can have coffee. No, that's fine. I think we can stop there.
Let's take questions from Mike.
So do you have a circuit, a supremacy experiment?
It's like maybe a loaded question. I think the.
No, I didn't load it.
Look, I guess. So what claim do I want to make? I think, yeah. So we have run circuits like these, hard, what I believe are hard to simulate circuits. So circuits once they're beyond about depth 12, based on these random graphs.
With 56.
We've run them with 56 qubits. What I'm showing here is not anything that's processed from the output of those circuits. We couldn't calculate, for example, the cross entropy of the sample drawn from that circuit.
Because you'd have to calculate.
Yeah. But this is meant to be evidence that when we run circuits like that, we believe that, if you look at this plot at around depth 12, that fidelity is representative of what fidelity we're, producing that state.
So the IBM team has been using the term quantum utility lately, and I was confused for a while on what it meant, but finally I clarified that it means we hope it's quantum supremacy, but if it's not, then don't blame us. So
I wouldn't say it like worked super well.
Call it that.
Be more generous.
It's fine.
Yeah, go ahead.
Maybe I missed it when you show those color plots, but how did you measure the complexity of trying to, optimize tensor contractions on this regime, on the largest circuits, and how does that compare to other experiments?
Yeah. So what I would say is that if you try reasonably hard to do the optimization over contraction, sort of methods or contraction trees, what you find is that by depth 12, you don't really see any improvement over the flops that you'd expect for state vector simulation. So, out kind of to the right of this line, the reason I drew the line there is that I think if you wanted to simulate circuits of that depth, at least as far as I can tell, there's really nothing short of state vector simulation you could do. But,
The other question is from Mike.
Yeah. So I guess, given these benchmarking results, sort of trying to understand, what would go wrong that would stop you from, let's say, being able to do a quantum supremacy or declare the quantum supremacy result in the near future, because it sort of feels like, maybe the fidelities aren't that well sort of representative. Maybe they're off by a factor of 10 or something like that, but that would still be enough to
claim to sort of make a claim about quantum supremacy. I guess, in some ways, there's really nothing that we would do differently if we wanted to claim quantum supremacy, other than, for example, these depth 20 circuits, they were actually, mirrored depth 10 circuits. We could take those circuits and we could, post the bit strings to a GitHub somewhere and let people try to simulate them. I think that's all that really would make That's the only difference you would need to make this quantum supremacy experiment. But other than that, I think in my mind, at least, the main thing one's trying to achieve in these experiments is give some indication that one is sampling, relatively faithfully for these hard circuits. And you can think of that as sort of, what, the mirror benchmarking results provide evidence of.
Anyone else? If not, stay quick again.